this second chapter of trigonometry, we were going to be extending our knowledge of the trig functions. In this lesson, we are going to look at double angle identities.
So like it says right up the top here, double angle identities are just special cases of the sum identities that we looked at in the previous lesson. So what I'll do is I'll just kind of introduce this. We're basically just going to give it to you, but I'll show you where they came from specifically here. Like, let's take a quick look at sine. So if I had the sine of alpha plus beta, we already know that this is going to be the sine of alpha cosine of beta plus the sine of beta cosine of alpha. That's the identity. Now, but what happens if instead of being alpha plus beta, what if this is alpha plus alpha? Okay. In other words, what if this is the sine of 2 alpha? So then this becomes the sine of alpha cosine of alpha plus the sine of alpha cosine of alpha. So in other words, the sine of 2 alpha is basically this expression twice. 2 sine alpha cosine alpha, which is exactly what you're seeing here as our first identity. Okay? Another one to look at here, and we'll just look at this second one here, and then we'll just assume the rest of them. The cosine of alpha plus beta is the cosine of alpha cosine of beta minus the sine of alpha sine of beta. Now, okay, we'll go that one step further here. What if these are the same angle? What if this is, in fact, cosine of alpha plus alpha? Well, then this is, this becomes the cosine of alpha minus the sine of alpha sine of alpha. Now, you should see something sort of familiar popping out here. But this becomes the cosine of 2 alpha. And this is going to be cosine of squared of alpha minus the sine, sorry, I put an alpha up top there, sine squared of alpha. Looks familiar, looks like another identity, but this is subtraction in between, and it's cosine squared of alpha minus sine squared of alpha. So that's the shortcut here. Now, because I've got a Pythagorean identity that also allows me to rewrite cosine squared of alpha and sine squared of alpha if I wanted to, there are in fact, wrong way, 3 different identities that can be equated to the cosine of 2 alpha, and here they are. And by the way, you're going to find as you go through this that these are the identities that we tend to test quite heavily. Specifically when we're dealing with equations, we work a lot here. Okay? Now, here's another one. The tangent of 2 alpha, okay, is going to be 2 tangent of alpha over 1 minus the tangent squared of alpha. And again, you can see where that comes from when you look at the sum of difference identities for tangent. Okay, so that's really not that hard to evaluate there, but yeah, so here they are, and you really just got to be familiar with that pattern so that you can recognize it, because these will all be given to you. You just got to be able to see them and recognize them when you're working through a problem, so that you know to go and say, oh, okay, yeah, cosine of 2 alpha, that could be any one of these 3. So it'll give you you give yourself a sense of what you need as you're working through a problem.
Write each of the following as a single trigonometric expression.
Okay, so to start off with here, we're going to work with 2 sine of 4x cosine of 4x. Notice the pattern here, compare it to what we've seen before. This is the same as 2 sine of angle cosine of angle, which is going to be the sine of twice that angle. So in this case, twice 4x. So this is really just the sine of 8x. Okay, let's move on. We'll just go through all of these here because this is going to be really quick. I've got the cosine of a half a minus the sine squared of a half a. Now this is the cosine, okay, this is going to be the cosine of 2 times whatever that angle is right there, and this is 1/2 a. So this is simply going to be the cosine of a. 2 times a half, they cancel out, we get a. 2 sine pi over 8 cosine pi over 8. Again, this is the same as the sine of 2 times that angle. And 2 times pi over 8 is simply going to be pi over 4. Okay, keep moving here. We've got this expression here, 2 tangent pi over 6 over 1 minus tangent squared of pi over 6. This is equal to the tangent of twice that angle, so 2 times pi over 6. And we know that 2 times pi over 6 is simply going to be pi over 3. 4 cosine of 10 degrees, sine of 10 degrees. Now, look, they're switching the order here. Don't let that throw you off here. Additionally, notice that the 4 there can be broken up into 2 times 2. Order does not matter, so I'm going to help myself out by changing the order here. And now I see that this is going to be 2 times the sine of twice that angle. So there's my identity here, and I know this is going to equal 2 times the sine of the angle there. So 2 times 10 degrees will be 20 degrees. So then this expression here is equal to 2 times the sine of 20 degrees. And so now you're going to see us start to play a little bit with the structure of the identity. Here's this next one. Cosine of 35 times the sine of 35. Now, first of all, the order is a little bit odd, but notice that the 2 is missing. Okay, now if the 2 is missing up here, just take a look at it. If the 2 is missing here, well, what did I do to it? I divided it over. So this has to be the sine of twice that angle divided by 2. So over here, whoops, where am I at here? This has got to be equal to the sine of 2 times 35 degrees, we'll deal with that in a second, all over 2. Or in other words, the sine of 70 degrees, and this whole thing divided by 2. Good. Now, 3 minus 6 sine squared of 6 theta. A lot going on there. But, and I see the pattern here, the minus the sine squared of something. So I notice that there's a common 3 here. I'm going to take that out, and I'm left with 1 minus 2 times the sine squared of 6 theta. Okay, well that 3 sits out front here, but this 1 minus 2 times the sine squared, that is the cosine of twice this angle. So this is going to be the cosine of twice 6 theta, or 3 times the cosine of 12 theta. Whoops, almost not see that. Good. Here, 8 sine 5 theta cosine 5 theta. Okay, well at least the sine and the cosine are written now in the right order. I want this to be a 2, so I'm going to split that up. And so now, I split that up into 4 times 2, so I've got the 2 there. So sine of 5 theta cosine of 5 theta. This, if I cover up the 4, this is all going to be the sine of twice that. So this will be 4 times the sine of twice that angle. Or in other words, this is going to be 4 times the sine of 10 theta. Whoops. And finally, 1 minus the 2 times the cosine squared of 20 degrees. Now, that seems right, but look at the identity up here. Whoops, look what it's equal to. Cosine of 2 alpha is equal to 2 cosine squared of alpha minus 1. You know what? This is in the wrong order. But I can change the order. I know I can change the order if I factor out a negative. If I take that negative out, then the 2 cosine squared of 20 degrees becomes positive, and the 1 becomes negative. And then I can change the order as I will there. So this becomes the negative cosine of twice the angle here, and 2 times 20 degrees is going to be 40 degrees. So that expression is equal to negative cosine of 40 degrees. And there you go, just a little bit of practice dealing with or identifying the identities and manipulating them to fit what we're seeing.
Write double angle identities for each of the following.
Okay, so when we talk about writing the double angle identities for these things, what I got to do is I got to look at the argument of these functions and take the 2 out to see what I'm left with. So this, for example, is going to be the tangent of 2 times 3x. And now I'm going to apply the double angle identity to that right there. So this is going to be equal to 2 times the tangent of 3x divided by 1 minus the tangent squared of 3x. That's what they're asking us to do, to look for the expression equivalent to that. Over here, I've got the cosine of 3 theta, and again, what I want to do is I want to pull the 2 out of that, so this will be 2 times 3 over 2 theta. And now I've actually got some choice as to what I'm going to do here. But you know what? We're going to go with the quickest one to get to here, which was the cosine squared of alpha, so 3 halves theta minus the sine squared of 3 halves theta. This is the first identity when you start doing the sum and difference identities. This is the first one that you get when you double up the angle inside cosine. And so there we go. Now, again, we could have used one of the three other ones. In fact, I mean, maybe we should. We should write this down here. This could be 1 minus 2 sine squared of 3 over 2 theta. Or it could be 2 cosine squared of 3 over 2 theta minus 1. They're all good. Now, over here, sine of a half a. So again, though, what I got to do is I got to pull out the 2 first. And then this becomes a over 4. And now I can write the identity. This will be 2 sine of a over 4 cosine of a over 4. Okay, so all I got to do is I just got to make sure that I can yank that 2 out to see for sure what angle it is that's being doubled in each of these identities.
Given that the sine of 2x divided by 1 minus sine squared of x is equal to 2 tangent of x, verify that the identity is true for pi over 4.
All right, well, to do the verification, what we got to do is we're going to plug in that angle. And you can see right here, we're going to plug in pi over 4. So here we go. This will be equal to the sine of 2 times pi over 4 all over 1 minus the sine squared of pi over 4. And then on the right-hand side, this will be equal to 2 times the tangent of pi over 4. And I'm going to do this one right away here because the tangent of pi over 4 is just 1. And 1 times 2 is just 2. So I can get really quick and easy. It's done. Okay, in the numerator here, this is going to be the sine of, well, 2 times pi over 4 is going to be pi over 2. So this will be the sine of pi over 2. Now, down here, I know that the sine of pi over 4 is root 2 over 2. And I'm going to be squaring that. The numerator here, now I'm going to have to work around here. This is going to end up being 1. The denominator is going to be 1 minus, okay, root 2 squared is 2. 2 squared is 4. So this is going to be 1 minus a half. Now, let's just think about this. 1 minus a half is a half. 1 divided by a half is, in fact, 2. And so there we go. We were able to show that the left side and the right-hand side are independently equal to the same thing. So we verified it. Okay? We verified it for pi over 4. Again, that doesn't prove anything. It just demonstrates that it's true for this one particular value.
Prove the identity.
All right, well, now, to prove this identity, we're going to start to replace pieces of it with things that we know that exactly equal to see if that we can get the same expression on both sides here. Now, I'm not going to work with a 2 tangent. Tangent's about as simple as that's going to get, but this one could be simplified a little further. Notice, for example, that the sine of 2x is a double angle identity, okay, and I know that that's going to be equal to 2 sine x cos x. Now, at the same time, I've got this 1 minus sine squared. Now, notice it's not 1 minus 2 sine squared, so it's not a double angle identity for cosine, okay? But it is cosine squared, okay? Think back to your Pythagorean identities, and I know that that's cosine squared of theta. Now, this is a significant step for me because I know that tangent ends in sine here, right? Sorry, cosine is what I meant to say. Tangent is sine of x over the cosine of x. So by making that substitution, I'm really putting that cosine in there. And now notice that there's a common cosine, numerator, denominator. So it's going to be 2 sine of x over the cosine of x, which is exactly what I got on the right-hand side. Those are equal to each other.
Determine the non-permissible values for either side of the identity.
All right, well, what we've been able to prove here is that this is, in fact, an identity. And so the restrictions that we're looking at should carry over from one to the other here. Now, notice that there is a tangent in this expression. Okay, now tangent's got the cosine in the denominator here. Well, actually, we can see it more clearly here. Notice that tangent has the cosine in the denominator, and that 1 minus sine squared is exactly the same as cosine squared. So again, we've got this cosine in the denominator here. So the restriction that we would normally get for tangent is going to hold on both sides because of that cosine in the denominator in both sides. So we can comfortably say that x can't equal pi over 2 plus n pi, where n is an element of the integers. That's the restriction in this case here, because remember, this is where cosine goes to 0. Can't let that happen.
Consider the expression sine of 2x over the cosine of 2x minus 1. What are the non-permissible values for the expression?
Okay, so in this case, to find the non-permissible values here, I'm just going to look at the denominator. The the numerator is not going to do it for me. Sine of 2x isn't going to create any non-permissibles for me. So I cannot let the cosine of 2x minus 1 equal 0, which means I cannot let the cosine of 2x equal 1. Okay, now let's just think about that. Where does cosine go to 1? Okay, think about the unit circle. We know that cosine is associated with the x-coordinate, and around the unit circle that's going to happen at 0 degrees, or multiples, or sorry, maybe I should do this in radians, 0 radians, and multiples of 2 pi added to that, or subtracted from that. So essentially what we're going to get here is I cannot allow 2x to be equal to multiples of, actually it should be multiples of 2 pi is really what it is. Multiples of 2 pi where n is an element of the integers. Okay, now I got to get to x here, so I'm just going to divide by 2. So x cannot be allowed to be equal to multiples of pi where n is an element of the integers. So that's the restriction on this identity.
Simplify the expression to one of the three reciprocal trigonometric ratios.
Okay, so this question wants me to simplify this expression, so I've rewritten it again here. Now, I got to be really picky and choosy about this one here. Sine of 2x, I really don't have much say over. That's going to become 2 sine x cos x. But I do have some freedom over what I use for cosine of 2x. Now, I'd like to simplify this thing as much as I can, so I'm going to be kind of clever here. I've got cosine of 2x, and I'm subtracting 1 from it. Now, let's go to the previous page here. Let's take a quick look at these guys again. Okay, so I've got a minus 1 coming out of that denominator there. So look at this right here. If I use this expression, okay, sorry, if I use the first one, I'm still going to have a minus 1 hanging out at back that I can't deal with. If I plug it into this one, I'm going to get a minus 2. Now, I might be able to work with that because I can factor out a 2 then. But look at this last one here. If this is cosine of 2 alpha, or 2 theta, this will become 1 minus 2 sine squared theta. Now, if I subtract 1 from that one and that one will cancel. I like that. I like that. So that's what I'm going to do. Oops, sorry, right here. I am going to write this as 1 minus 2 sine squared x minus 1. Now, the ones will cancel, and now I'm left with 2 sine x cos x over negative 2 sine x sine squared of x. So the 2's will cancel. It's still going to be negative. One of the cosines will cancel, and I'm left, cosines. Sorry, I looked right at it, and I said it wrong. Sines will cancel, and I'm left with cosine of x over the sine of x, and that's just the negative cotangent of x. So that's what they wanted us to simplify it to.
If cosine of A is equal to 12 over 13, and angle A is in quadrant 4, find the exact value of the sine of 2A.
Okay, well, to answer this question, remember, I want the exact value of the sine of 2A. Well, to get that, remember that the sine of 2A is going to be the sine of A cosine of A. Well, I already know the cosine of A. Okay, so I already know this is going to be 2 times something times 12 over 13. So now let's just see what information we're given here. We know that A is in quadrant 4. Okay, well, that's important here. So A is in quadrant 4. And we know that the cosine is 12 over 13, which means the x value is 12. The hypotenuse here is 13. And if you don't recognize this, you can certainly use the quadratic formula. But if the hypotenuse is 13 and one of the sides is 12, the other side is 5. Okay? That's a Pythagorean triplet. It's a common triangle that gets used here. Now, more than this, though, because it's in the fourth quadrant, I know that this is also going to be negative 5. So now think about this. The sine of this angle is going to be the y-coordinate over the r, or the radius, so negative 5 over 13. So negative 5 over 13. Okay, now, here we go. I can multiply this out. 2 times negative 5 times 12 is going to be, it's going to be negative 120. And 13 times 13 is 169. And so there we go. That's the expression that we're looking for.
Prove each of the following identities. 1 plus the cosine of 2x divided by the sine of 2x is equal to the cotangent of x.
Okay, so remember, to prove these identities, what we're going to do is we're going to do some work on both the left-hand side, the right-hand side, and show that they're equivalent to each other. Now, I am going to do most of my work on the left-hand side because there's a lot more going on here. But on the right-hand side, notice that this is going to equal simply cosine of x over the sine of x. I'm much more likely to bump into this before I bump into cotangent. Now let's take a look here. My denominator is going to be easily the sine of x, sorry, 2 times the sine of x cosine of x because of that identity there. Now, I've got these two terms in the numerator. I probably don't want those. So what I'd like is a single term there. So I'd like to get rid of that 1 here. So I'm going to replace the cosine of 2x with something that's going to have a subtract 1 in it. And if you think about it, that's going to be the 2 times the cosine squared of x minus 1. So the 1's will cancel, the 2's will cancel, and I'm going to be left with, and one of the cosines will cancel. A whole lot cancels here. And I'm simply left with a cosine of x over a sine of x. It just really falls into my lap quite quickly once I make that substitution. But I got to make the right substitution for the cosine of 2x. Now again, my motivation for doing that is I wanted the 1 to disappear. So I chose the identity that was equal to the cosine of 2x, the one that had the subtract 1 in it. Okay, because I can kind of think ahead what I want to happen here. I want it to look like this. I needed to get rid of that extra piece.
The sine of 2x divided by the sine of x plus the cosine of 2x plus 1 divided by the cosine of x is equal to 4 times the cosine of x.
All right, so here we go again. We're going to split this up into 2 parts here. There's really nothing I can do on the right-hand side, but there's a lot going on over here. So, but notice that on the right-hand side, I want to be left with 4 cosines here. So let's just take a look at what's going on here. Now, I do have options with the cosine of 2x, so I'm not quite sure what I want to do with this yet, but I really don't have any choice here. Sine of 2x is going to be 2 sine x cos x divided by the sine of x. Oh, now, okay, now look at that. These signs, even before I do that second term, these signs are going to disappear, and I'm going to be left with 2 cosines. Well, I want 4 of them. So I essentially want this to become 2 cosines as well. So I know that cosine of 2x can be cosine squared minus sine squared, 2 cos squared minus 1, or 1 minus 2 sine squared. Well, I want the one that just has the cosine in it, because I just want to be left with cosines here. So this is going to become plus 2 cosine squared of x minus 1 plus 1. Whoops, sorry. That's not very clear, so I'm going to move that line over a little bit. So this is going to become minus 1 plus 1 over the cosine of x. Now, the minus 1 plus 1 cancel, okay? One of these cosine factors therefore cancels, and I'm left with 2 cosines. So this is 2 cos x plus 2 cos x. And so what we've got here is 4 cos x, which is exactly what I get on the right-hand side. So I proved it.